Yes. So, good evening to all the participants who will be joining for today's session and who will be joining the session later on, and those who will be watching the video recording. I welcome you all to this live interaction session, session 9 of this NPTEL course, Advanced Reinforced Concrete Design. So, today we are going to be discussing about some of the sample problems, how to solve the theoretical and the numerical problems related to the behavior of reinforced concrete columns. Without any further delay, let us start today's session. I'm going to turn off my video and then I'm going to start the session for today. Yes, so I welcome you all to this uh, live interaction session of the NPTEL course Advanced Reinforced Concrete Design for the year 2025. And the course instructor is Professor Surya Prakash from IT Hyderabad. And presently, we are in the week 9 of this live interaction session. So, another 3 weeks to go in our course. And yes, this session is presented by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMR fellow in the Department of Civil Engineering at IIT Delhi. And this will be the agenda for today's session. So, as always, we will be solving some sample problems, right? As we have been doing from the very first week of the live interaction session, we'll be solving some sample problems which will help you to solve the assignment problems, understand the concepts of this NPTEL course in an in-depth manner, and then to help you in solving the examination questions. So this week we dealt with we started the module 8 concerning the behavior and design of reinforced concrete columns, and broadly we have studied the first two parts of this particular module. So I'm just going to give an outline of what was covered in these two parts of module 8. In module 8.1, we studied the different types of columns and the concept of effective length. So, how are you going to classify the columns depending on the constituent materials? For example, we had the reinforced concrete column, and then we had the uh, concrete encased structural steel column, and so on. And then, also depending on the height, we are going to classify the columns as uh, short columns or slender columns. So, which is why it is very much important to uh, determine the effective length of the column so that we can predict the behavior and design the column accordingly. So, as I mentioned earlier, we looked into the classification of columns and then what is meant by the effective length of the column. And then we also um, discussed about the distinction or the differences between a sway and a non-sway frame. And then the we also determine the stability index, which helps us to determine whether a particular frame is a sway frame or a non-sway frame. Okay. And then in module 8.2, we looked into the codal provisions and the aspects of the behavior of short axially loaded column. So in particular, we we basically defined what is meant by the slenderness ratio, and we looked into the concept of minimum eccentricity. Okay, what is meant by the minimum eccentricity for columns, and what are the IS code provisions for the reinforcement detailing, and then further we also looked into the actual capacity of concentrically loaded columns. That is, we designed, we looked into some numerical problems based on the design of concentrically loaded reinforced concrete columns. And then we also considered the design of reinforced concrete column with tie reinforcement, and design of reinforced concrete column with helical or spiral reinforcement. Okay. Uh, so the rest of the module, that is the remaining parts 3, 4, and 5 of this module, is going to be taken up in the next class. So for today's live session, let us go ahead and solve some of the sample problems on uh, the topics that are enumerated in this particular slide. Okay. So with that introduction, let us proceed to the sample problems. Right. So let us look at the first problem now. Right. So in the question one, we have I have given the framing plan of a multi-story building. Okay, and here we need to actually this is actually a big problem. So we are going to be taking up individual aspects of this column and look how we are going to uh, do the design of this reinforced concrete column. Okay, so I'm going to start reading the problem now so that let us actually determine what needs to be calculated in this particular numerical problem. Okay, so the columns in general of this plan of the multi-story building have a size of 300 millimeter by 400 millimeter, and the longitudinal beams along the x-axis. The x-axis is running in the horizontal direction in this particular uh, plan, right? So that is having a size of 250 by 600 millimeter, and the transverse beams have a size of 250 by 400 millimeter. That is running along the y-axis of this framing plan. And then the story height is 3.5 meter. So the question is to determine the unsupported length of the highlighted column about the x-axis and the y-axis. Okay. So the question is determine the unsupported length of the highlighted column, that is highlighted by this yellow circle over here. What is the unsupported length of the highlighted column about the x-axis and the y-axis? Okay. So the important term over here, I would say, is the term about. Okay. So I'm not asking what is the unsupported length along the x-axis. I'm asking about the x-axis. Okay. That is, if it were to bend about the x-axis, okay, that is along this direction. So about x-axis means along y-axis, and about y-axis means along the x-axis. Okay, so we need to determine the unsupported length of the highlighted column about the x-axis and the y-axis. So the reason why I am describing it as above x-axis and above y-axis is that because the effective length is going to be determined using the same terminology or the same concept. We are going to determine the effective length of the column above the bending axis. Okay, which is why we need to determine the unsupported length above the x-axis and the y-axis. Okay, so we'll wait for a few seconds, then we look at the solution to this problem. Okay, so let us look at the solution now, right? So, as I already mentioned, let us solve the unsupported length about the x-axis. So, unsupported length above the x-axis means unsupported length along the y-axis. Okay, so if the column were to bend along the y-axis, what would be the unsupported length? Okay, so what we need to do essentially is that we need to determine we need to find out the story height. Okay, so from the story height, we need to deduct the height of the beam that is along this direction. Okay, that is how you find out, and we know that the beam along the transverse direction has a depth of 400 millimeter. Okay, it becomes more evident in the next slide that we're going to see, right? So in this, here it represents section AA. So section AA is a section taken across one of these transverse beam. So the unsupported length about the x-axis, let me write down the un you need to pardon me if the handwriting is not very legible. So about x-axis is equal to c. So the floor to floor height is 3.5 meter. Okay, so that is 3,500. Let's express in terms of millimeter minus the depth of the column in the transverse direction, that is 400 millimeter. Okay, right. So that gives us a value of 3,100 millimeter. Similarly, we need to find out the unsupported length above the y-axis, right? So this unsupported length we are going to be using in determining the um, effective length, and the effective length basically, depending on that, we can classify it as a short column or a slender column, and then we can perform the design accordingly. So about the y-axis means along the x-axis. So let us consider the floor to floor height, that is 3,500, minus what is the depth of the beam along the longitudinal direction, that is 600 millimeter. Okay, so the unsupported length about the y-axis is 2,900 millimeter. So the correct answers are 3,100 millimeter and 2,900 millimeter. Okay, so option A is the correct response. Now let's proceed to the next question. Right. So for the multi-story framing plan given in question 1, determine the cumulative stiffness of the columns along the uh, x-axis and the y-axis. Okay, the hint is stiffness of one column is given by IC divided by HC, where IC is the moment of inertia of the column along the direction considered, and HC is the uh, height of the column. Okay, now let us proceed to determine the cumulative stiffness. Okay, so here again we are moving to along the x-axis and along the y-axis. Okay, so keeping that in mind, let us proceed. Okay, so we have along x-axis, right? We need to determine the cumulative stiffness along x-axis. Okay, so we need to determine the cumulative stiffness of the column along the x-axis. So let me draw the plan, I mean the column dimensions in plan, right? So here we have the x-axis and then here we have the y-axis. So if you're considering um, along the x-axis, right? So then it would be, I'm going to write the dimensions over here. So this vertical dimension is 400 millimeter and this horizontal dimension is 300. So 3, okay, 300 millimeter, right? 300 millimeter. So if you're considering the stiffness along the x-axis, then this would be the b value, that is the width, that is 400 by 300 cube divided by 12. That would be the moment of inertia. Okay, that is 400 by 300 cube divided by 12, right? Divided by hc. Hc is 3500, right? And we are going to multiply this by the number of columns. Okay, so how many columns are there in this framing plan? That is 1, 2, 3, 4. That is three base along the x-axis and three base along the y-axis. That is four columns along the x-axis and four columns along the y-axis. That will give 16 columns, right? So multiply this by 16 and then we get this cumulative stiffness of, okay, let me write down the expression for the cumulative stiffness, right? I'll take a different color. Cumulative stiffness given by IC by HC, IC by HC. So that gives us a value of 4114.3 into 10 to the power 3 millimeter cube. That is the value of cumulative stiffness along the x-axis. Now for the y-axis, a slight modification along y-axis. So along the y-axis, okay, so along the y-axis here 300 millimeter would be the width and 400 millimeter would be the depth. That is calculate accordingly, right? That is 300 by 400 cube divided by 12. So for the value of HC, we are considering the floor to floor height. Multiply this by 16 columns. Okay, this gives us a value of how much? 7314.3. 7314.3 into 10 to the power 3 millimeter cube. Okay, so the answers are 4114 and 7314. 7314. Okay, so option B is the correct response. Moving on, let us look at the third question now. For the multi-story framing plan given in question 1, determine the cumulative stiffness of the beams along the longitudinal and the transverse directions. Okay, longitudinal refers to the x-axis and transverse refers to the y-axis. So earlier we determined the cumulative stiffness of the columns along both the directions. Now we need to determine the cumulative stiffness of the beams along both these directions. Okay, and again the hint is given with stiffness of the beam is given by IB by LB, where IB is the moment of inertia of the beam, and then LB is the uh, center to center span. Okay, let us proceed now. Right, so again it is along the x-axis and the y-axis. Cumulative stiffness. Cumulative stiffness of the beam that is given by IB divided by LB. Okay, so first we'll do along the x-axis, right? Along x-axis. So that gives us what is the value of IB. So let us remember that the dimensions of the beam in the longitudinal direction, that is 250 by 600. Okay, so you can say that these are the primary beams and these are the secondary beams because the depth is 400 millimeter. Right? So IB would be 250 by 600 cube divided by 12. That is IB. And what is the center to center distance? That is 6 meter. Right? Yeah. We'll express all the terms in terms of millimeter, Newton and millimeter. Right, 6,000. Okay, and then multiply that by the number of beams. Okay, so we have how many beams along the x direction? 1, 2, 3, 1, 2, 3, 4. Okay, so there is 3 into 4, that is 12, multiplied by 12, and that gives me a value of how much? 9,000 into 10 to the power 3 millimeter cube. Moving on, let us determine the cumulative stiffness along the y-axis. Along y-axis, so here, what is the dimensions of the beam along the transverse direction? 250 by 400. Okay, let me check. Yeah, 250 by 400. Let's plug those values, determine the cumulative stiffness, that is 250 by 400 cube divided by 12. Yeah, and here the difference is we need to take into account the span, center to center span along the y direction, that is 4 meter. Convert it into millimeter, multiply it by the total number of beams. So here also, what are the number of beams along the transverse direction? 1, 2, 3 multiplied by 1, 2, 3, 4, that is 12. Okay, hence this 12. And for that we get a value of 4,000 into 10 to the power 3 millimeter cube. So that is the cumulative stiffness of the longitudinal and the transverse beams, 9,000 and 4,000. So option E is the correct answer. Let's proceed to the next question now. So, so we are basically building off the previous questions. and increasing the complexity of the problem in order to understand the behavior of this framing plan uh, and the columns. Okay, so that is the idea. And in question 4, the question is that the multi-story framing plan given in question 1, for that framing plan, determine the lateral flexibility, that is delta u by hu, or which is also known as the story drift per unit story shear. Okay, we need to determine the value of delta u by hu. Okay, which is called as the lateral flexibility or the story drift per unit story shear of the story along the longitudinal and the transverse directions. Okay, so here we need to look at one term, that is flexibility. So if we look at the stiffness, so stiffness is usually it is the opposite. I mean it is the other way around. So let us try to what are the units for this particular term. We have delta u. Okay, so delta u by hu, right? So delta u is the lateral displacement of this framing plan along any uh, lateral direction, that is x direction or the y direction, and hu is the story shear. Okay, so this is given. The units are let's say millimeter. Sorry about that. Millimeter by Newton, right? Millimeter per Newton. So hence it is called as flexibility. But on the other hand, if you are trying to express the stiffness of the framing plan, it usually tends to be in the units of force per displacement, that is Newton per millimeter. Okay, so now let us proceed to find out the value of this term, that is delta u by hu. And then it is given that for the columns we need to consider M25 grade of concrete, and for the beams we need to consider M20 grade of concrete. Okay, let us proceed further. So this term delta u by hu is given by this particular equation, that is h square divided by 12 EC column summation of IC by HS, right? So that is the cumulative stiffness of the column, and then here we have HS square divided by 12 EC B summation of IB by LB, which is the cumulative stiffness of the beams, which we have already determined in the previous questions. Okay, so let us determine the uh, value of this story drift per unit story shear, or delta u by hu, along both the lateral directions, right? Let us consider the value along the x-axis first, right? Along x-axis. Okay. Let us calculate the value. Let us write down the values at least over here. Okay. I'll take this color. HS is the story height, so that is 3500 millimeter. Millimeter, right? Then we have this EC or column, that is 5000 square root of FCK, that is 25000 or 25,000 MPa. Then we have elastic modulus for the beam, right? That is 5000 square root of 20, which gives us a value of how much? 22360.7. 22360.7 MP, right? And then we are going to substitute these values accordingly as we proceed in the problem, right? So let me plug these values in the equation for delta U by HU. That is how much? 3500 square divided by 12 into 25,000. What is the value of uh, the cumulative stiffness for the columns along the x direction? That is 4114.3, right? 4114.3 into 10 to the power 3. Okay, so that is the first term that we have. Now let us consider the second term, that is 3500 square divided by 12 into 22360.7. What is the value of the cumulative stiffness of the beam along the x direction? That is 9000 into 10 to the power 3. Okay, 9000 into 10 to the power 3. Okay, so I'm just going to leave it at this point. We're going to write the answer later on. And let us proceed to write the equation for the uh, value of delta U by HU along the y-axis. Okay, along y-axis. That is delta U by HU is equal to, again, here it is 3500 squared, so that is the same for all the terms, divided by 12 into EC column, that is 25,000, multiplied by cumulative stiffness along the y direction, right? That is 7314.3. 7314.3 into 10 to the power 3. Okay, plus 3500 square multiplied by 12 into 22360.7 multiplied by the cumulative stiffness of beam along the transverse direction, that is 4000 into 10 to the power, right, 10 to the power 3. This is 4000. So we'll get the value of delta U by HU along the y-axis. So what are these values? I'm getting a value of, let me take another color. Along x-axis it is 1.5 into 10 to the power means 5 millimeter per Newton, and along the y-axis it is 1.7 into 10 to the power minus 5 millimeter per Newton. Okay, so it is along x it is 1.5, into, into 10 to the power minus 5, and along y-axis it is 1.7 into 10 to the power minus 5. 1.5 and 1.7. So option D is the correct response. Let us proceed to the next question now. Okay, so once you have determined the value of delta U by HU, determine the stability index, right? Determine the stability index of the framing plan along the x-axis and the y-axis. Okay, so why do we determine the stability index? So we look at later stage also. So if the stability index is less than a particular value, right? Let's say 0.04. I think that is the threshold value. If it is less than 0.04, we may classify the frame as a non-sway frame. Okay, which is why it is important to uh, determine the stability index. Okay, and the hint that is given is the equation for stability index Q is equal to sigma pu by hs multiplied by delta u by hu. Okay, and then here sigma pu refers to the total sum uh, carried by the columns, the total sum of the load carried by the columns, or in other terms we can say that it is the uh, load of the floors uh, above the columns considered. Okay, if you're considering, let's say, column at a particular story, then the sum of all the above stories combined. Okay, that is the definition of sigma pu. Okay, let us proceed to find out the value of stability index now along the x-axis and the y-axis. Yeah, so here we have the equation. So along stability index, index q, now along the x-axis. So here, in order to determine the value of sigma p, we are having some data. Okay, sigma pu, that is summation of all the axial load carried by the column, that is given by 35 kPa multiplied by the area of the framing plane. Okay, so 35 multiplied by 18 by 12. 35, sorry about that, 35 by 18 by 12, which gives us a value of how much? 7560 kilonewton, right? 7560 kilonewton. That is the value of sigma pu. Now let us proceed to find out the value. 7560 into 10 to the power 3, because remember we are going to convert all the force units into Newton and all the length units or the displacements units into millimeter. Okay, HS is the story height, that is 3500, 3500 multiplied by delta u by hu along the x-axis, that is 1.5 into 10 to the power minus 5, right? Yeah, 10 to the power minus 5. Okay, so let us keep the value here, qx, box it. Okay, along y-axis, that is the sigma pu remains the same, 7560 into 10 to the power 3 divided by 3500 multiplied by 1.7 into 10 to the power minus 5, right? So here we have the value of q. So let us write the answer in another color. So I got a value of 0.0324, 0.0324 along the x-axis and 0.0367 along the y-axis. 0.032, 0.037. So option C is the correct response. Moving on. Okay, so once we have determined, yeah, one more conclusion that we can draw from this is that since here let us read this particular clause from IS 456 Annex E. Okay, if Q is less than equal to 0.04, then the column in the frame may be taken as no sway column. Otherwise, the column will be taken as a sway column. So since both the stability index along both the y-axis and the x-axis and the y-axis, both of them are less than 0.04. So the column can be taken as a non-sway column. Okay. Let us proceed to the next question. For the multi-story framing plan given in question 1, consider the highlighted interior column. That is, this is the highlighted interior column. Determine the effective length of the column about the major axis and the minor axis using annexure E of IS 456-2000. Okay, so I'm just going to draw a sort of magnified view of this column, or the diagram of the column in plan, right? And then we are going to call this stronger axis as the major axis, right? Just because the depth is 400 millimeter over here, and the bending about this axis is more difficult. So x-axis is the major axis and y is the minor axis. Okay, and that happens to coincide with our global axis. Okay, so we need to determine the effective length of the column. So how do we determine the effective length? So basically this effective length is given by the unsupported length multiplied by the k factor. So that k factor we can obtain using the IS 456. Okay, uh, please give me a few seconds. Okay. Yes, I guess we are good to go now, right? Hmm. So basically, what we need to do is we need to determine this value of beta one and beta two. So essentially, it is given by this equation, that is sigma IC by Hs for the joint considered, divided by sigma IC by Hs plus sigma zero point 0.5 IB by LB. So what we are doing is, for this particular joint that we are going to consider, we need to determine the cumulative stiffness of the columns and the beams that are meeting at that particular joint, and obtain the value of beta 1 and beta 2. So once we obtain the value of beta 1 and beta 2, then we can go ahead and proceed to determine the value of k. Okay, the effective length ratio, or the k, right? And then uh, the the product of this effective length ratio, or the effective length factor k, and the unsupported length, that gives us the value of the effective length. Okay, so this you can see that the values of beta 1 and beta 2 are in the y-axis and the x-axis respectively, right? So let us proceed to calculate the value of beta 1 and beta 2, right? I think it is better if we can just copy and paste this figure to help us in our calculations. Copying this, I'll copy the highlight with that. Yeah, let's move it. Yes, this column. Okay, so let us proceed to determine the value of beta 1 and beta 1 is equal to beta 2. Okay, now do we have the required color? Okay, let us first consider along the x-axis. Okay, along the x-axis. Right. So we have beta 1 is equal to beta 2 is equal to, okay, along the x-axis. So basically, the columns are, we need to consider two columns, one that is projecting above from this floor plan, and one column that is projecting below this floor plan. So IC is 400 by 300 cube, right? Yeah, 400 by 300 cube divided by 12 divided by HS. HS is, yeah. Uh, okay, I think first we need to determine the value of these individual terms. Then we can proceed to determine the value of beta 1 and beta 2. Okay, so let us find out first the value of sigma IC by HS. IC by HS for the joint. Then we'll find out the value of sigma IB by LB for the joint. Okay, divided by 3500. So that gives me a value of how much? Oh, we have to multiply this by 2 because, as I said, at this joint there are two columns that are meeting, that is above the considered plane and below the considered plane. Okay, this gives me a value of how much? 514.3 into 10 to the power 3. 514.3 into 10 to the power 3 millimeter cube. Okay, I'm just going to leave the unit here. Okay, because of the space constraint. Now IB by LB, that would be along the x-axis. These are the primary beams, that is 250 by 600 cube divided by 12. And then at this joint we are having two beams that are joining in the x direction. Okay, multiplied by 2 and divide the value by LB. What is the span length? That is 6 meter. Yeah, 6 meter. Okay, this gives me a value of 1500 into 10 to the power 3. That's interesting. Millimeter cube, right? And then we can substitute the value of this IC, sigma IC by HS and sigma IB by LB in this equation. And then we get the value of beta 1 is equal to beta 2 as, let us skip into 10 to the power 3 term because they are going to eventually get cancelled out. Okay, that is 514.3 divided by 514.3 divided by 514.3 plus half of 1500. So we get the value of beta 1 and beta 2 as 0.407. Okay, let us proceed to the chart in annexure E. Okay, so we have beta 1 and beta 2 as 0.407, 0.407. Okay, corresponding to corresponding to beta 1 0.407 and 0.407, we'll get a value of about 0.64. Okay, we know that the effective length ratio, that is kx in this case, that is 0. It is between 0.62 and 0.65. Let us consider it as 0.64. Okay, so kx is 0.64. Now we'll proceed to do the same operation along the y-axis, right? Let us proceed to do the same operation along the y-axis. I'll take a different color, right? So we have sigma IC by HS is equal to, along the y-axis, right? So we have uh, 300 by 400 cube, right? 300 by 400 cube divided by 12, and again there are two columns meeting at the joint, divided by 3500. Then we have sigma IB by LB, the joint. So we're considering the beam in the transverse direction, that is 250 by 400. 250 by 400 cube divided by 12. And what is the span in the transverse direction? That is 4 meter. 4000 multiplied by 2. Okay. So sigma IC by HS is 914.3 into 10 to the power 3, which I'm leaving because that will get eventually cancelled out in the equation, in the simplification. And sigma IB by LB is 666.7, 666.7 into 10 to the power 3. Okay, now let me write it here so that those who are solving later on will not get any doubts or get confused. So when we do the same operation of these values, that is beta 1 is equal to beta 2 is equal to sigma IC by HS divided by sigma IC by HS plus sigma zero point 0.5 IB by LB. When we perform the same operation using these terms, we get the value of beta 1 and beta 2 as, I'm going to take a different color so that there is no confusion. Mm, mm, Beta 1 is equal to beta 2 is equal to 0.733, 0.733. Let us go to the chart and find out the value of ky, right? I'm going to write ky over here, 0.73, 0.73 and 0.73. So the value lies between 0.80 and 0.85. Okay. So let us take the value of ky as 0.82. Okay. Ky is 0.82. So now once we have the value of kx and ky, we need to go back to the unsupported length along the x and y axis. Okay, unsupported length along the x axis is 3100 and unsupported length above the y axis is 2900. Okay, we need to use this and the k factor to arrive at the effective length of the column. Okay, right. So we have um, yeah, effective length. Let me call it as yeah, lex. Lex is equal to kx into lx. That is the effective length above the x-axis, right? What is kx? Kx is point. Yeah, so basically what we are doing is here along x-axis means about x-axis, and here along y-axis means about x-axis, along x-axis about y-axis, along x-axis about x-axis. Okay, so for this we need to consider, so this becomes kx, in fact not ky. Okay, that is the small correction which I request you to make. Okay, there's a small correction over here, so it is not kx, it is in fact ky, and here it is not ky, it is in fact kx. Okay, so we have kx is 0.82 into 3100, that is 2542 millimeter. 2542 millimeter LEX. Similarly, LEY is equal to KY into LY. So, what is the value of KY? 0.64. Yes, 0.64 into 2900. Okay, so LEY is how much? 1856 millimeter. 1856. So LEX and LEY are 2442 and 1856. 2442, sorry, 2542, right? Yeah, 2542, 1856. So option B is the correct response. Okay. So with that, let's proceed to the next question now. Right. For the highlighted interior column considered in question 6, right, determine the slenderness ratio about the major and the minor axis. Okay, and then do we design it as a short or a slender column as per IS 456. Okay, this is the highlighted column. No, so now how do we determine the slenderness ratio about the major and the minor axis? Okay, so we have this yeah, this is the major axis xx, and we have the minor axis slenderness ratio. Okay, um so slenderness ratio about the x-axis is LEX by D. Okay, slenderness ratio about the y-axis is LEY by B. Okay, so we have LEX by D is 2542, 2542 divided by 400, and LEY is 1856, 1856 divided by 300, okay, which gives us a value of 3 point, sorry, 6.36 and 6.19. 6.36 and 6.19. Okay, and yeah, so as per this clause 25.12 of IS 456 2000, if both the slenderness ratios about the local x-axis and the local y-axis are both less than 12, are both less than the value of 12, then they can be designed as short compression members. Okay, right? So slenderness ratio about the x-axis and the y-axis are 6.36, 6.36 and 6.19. So option C is the correct answer, and it can be designed as a short column. It is classified as a short column. Okay. Now the next question is, for the interior column considered in question 6, determine as per the IS code the minimum eccentricity about the major and the minor axis. Okay. Does it satisfy the provisions of clause 39.3 of IS 456 2004 short axially loaded columns? So again, let us go back and draw the sketch of this interior column, right? So this is the fundamental, we need to identify the axis, the local axis, so that we can uh, determine its behavior, right? X, Y, Y, okay, and the dimensions are, the depth is 400 and the width is 300 millimeter. Okay. Now the minimum eccentricity, right? Minimum eccentricity is given by L by 500 plus dx by 30. Okay. Let us take a few seconds to understand what it actually means, right? Okay. So let us try to understand the physical meaning of what is this minimum eccentricity, right? I'm going to draw the sketch over here also. Let me see if I can copy paste it, right? We'll keep the annotations, right? Okay, let us go back to the question now. So for the Ex min, that is the minimum eccentricity above the x-axis, right? Let us calculate that value. Ex min is equal to the unsupported length above the x-axis, that is 3100 divided by 500 plus the depth above the x-axis. The depth above the x-axis means 400 millimeter, right? 400 divided by 30. So that gives us a value of 19 point, how much? 19.8. Okay, that is 19.5. Or it has to be 20 millimeter, whichever is greater. So for that reason, we are going to take the minimum eccentricity about the x-axis as 20 millimeter. Okay, then we have Ey min is equal to unsupported length divided by 500, 1900 divided by 500 plus the depth about the y-axis. The depth of the about the y-axis is 300 millimeter, right? 300 divided by 30, which gives us a value of 15.8. 15.8 millimeter. But we know that it is less than the value of 20 millimeter, so we're going to take Ey minimum as 20 millimeter. So the eccentricity about both the minimum eccentricity about both the x-axis and the y-axis both are 20 millimeter each. Okay, so option D seems to be the correct answer, but let us try to evaluate what is the next part of the question. Okay, so does it satisfy the provisions of clause 39.3 of IS 456 for short axially loaded columns? So let us see what it says, right? Though the minimum eccentricity should not exceed 0.05 times the lateral dimension. Okay, let us try to see the 0.05 times the lateral dimension along both these directions, right? So yeah, I'm going to write that in a different color. 0.05. So here we are finding out about the x-axis. Let us consider the local y-axis. 0.05 times 400, right? So that gives us a value of 20 millimeter. So it is not exceeding, right? Ex min and 0.05 d are both the same. Now let us find out for the Ey. Ey is eccentricity about the y-axis, that is this dimension, that is 300 millimeter. Okay, 0.05 by 300, that gives us a value of sorry, yeah, 0.05 by 300 gives us a value of 15 millimeter. So here Ey min is exceeding the value of 0.05 the lateral dimension, or 0.05 into b. Okay, so this criteria about the y-axis is not satisfied, which means that if this dimension we are able to satisfy by modifying the dimension of the column from 300 millimeter to 400 millimeter, we should be able to satisfy the this criteria for short axially loaded columns in terms of the minimum eccentricity. Then we can apply this equation. Okay, so in the current state with the dimensions of 300 by 400 millimeter, we cannot apply clause 39.5. Because why? Because this minimum eccentricity is exceeding the value of 0.05 times the lateral dimension about the y-axis. Okay, so 20 millimeter Okay, uh, the minimum eccentricity about the y-axis that is exceeding the value of 0.05b. So for that reason, we cannot proceed and apply the value of apply the uh, design the column as per clause 39.3. It cannot be designed directly in the current dimensions as a short actually loaded column. So option B is the correct answer. Okay, we'll proceed to the next question. Now, the interior column considered in question 6, the same interior column that we considered in the question 6, we have modified the dimensions to 400 by 400 millimeter. Okay, and it is subjected to a service load of 1500 kilonewton. Now we need to determine the area of the longitudinal reinforcement as per IS 456 2000. So as I already mentioned, right? So if we are able to increase the dimension to the 400 millimeter, then we can easily apply this clause 39.3. Okay, now let us proceed to design the column as per this particular clause for short actually loaded column. Okay, let us write down all the pertinent data now. Hmm. Okay, I'll write down the data here and then I can just copy paste it in the next slide, right? Change the color. Okay. So P is 1500 kilometer, right? So PU is equal to 1500 into 1.5, that is 2250 kilometer. Okay, and then we have FCK is equal to 25 MPa and Fy is 415 MPa. And B and D both are 400 millimeter. B is equal to 400 millimeter with the annotations. Now we can rewrite this particular equation as follows. PU is equal to 0.4 FCK into AG. So here AC is the area of concrete. We can write it in terms of the gross cross-sectional area divided by 0.67 Fy minus 0.4 FCK into AS. Okay, so what we need to determine is the uh, value of AS. Okay, we know pretty much all the other values. Let us proceed to do that now. 2250 into 10 to the power 3 is equal to zero point 0.4 into 25 into 400 square plus 0.67 into 415 minus zero point 0.4 into 25 multiplied by AS. So AS is equal to, or AC is equal to 2425 mm square. 2425. Okay, so as per that, option C is the correct response. Okay, now let us proceed to mm, design the lateral ties for this particular column. Okay, now before proceeding to the next part, let us determine the diameter and the number of longitudinal reinforcements. Okay, now 2425, 2425 divided by pi by 4 of 20 square, which gives a value of 7 point. So provide 8 of 20 dia Fe 415 longitudinal rebars. Okay, that is the answer. So let us proceed to determine the diameter and the lateral spacing of the spacing of the lateral ties, which is both structurally safe and economically efficient. Okay, it is quite simple, right? So the tie diameter, it should be greater than or equal to both of these values. So the first value is uh, the diameter of the longitudinal reinforcement, having the maximum diameter. So where we are providing 20 bars or 8 bars, all of 20 diameter. So 20 divided by 4 is 5 millimeter, or it can be 6 millimeter. So whichever is greater. So uh, usually in the construction practice in India, we tend to follow 8 rebars, 8 rebars of Fe 415. Now we need to determine the spacing. So the spacing has to be the least of these three values. Okay, so spacing is lesser than equal to D is uh, ST is less than equal to the least of these three values, right? So first we have the value of D, right? D is the least lateral dimension, that is 400 millimeter. The second part is 16 into the diameter of the longitudinal rebar having the minimum dia, that is 16 into 20, that is 320 millimeter, or it has to be at least 300 millimeter. So out of all these three values, we need to pick the lowest value, that is 300 millimeter. So provide 8 diameter stirrups at 300 millimeter center to center. Fe415. Okay. So option F is the correct response. Okay. So now we solve the problem for a reinforced concrete column having lateral ties. Now let us proceed to design a circular reinforced concrete column having a spiral or a helical reinforcement. So before that, let us proceed to calculate the basic data pertaining to the problem. Okay, we have a circular reinforced concrete column of 400 millimeter diameter. If this column is part of a braced frame and it is unsupported over a length of 3.4 meter, determine its slenderness ratio. Okay, and for determining the slenderness ratio, we can take the value of K or the effective length factor as 1. Okay, so there is no change in the length of the unsupported length, right? So let us Let me simply write it as LE, the effective length, because it is uh, you can say the circular cross section is symmetric and uniform about both the x-axis and the y-axis. So LE is equal to k factor into the unsupported length, right? That is 1.0 into 3400. Okay, so the effective length is 3400 millimeter. So now what is the value of the slenderness ratio? The slenderness ratio is equal to LE by D, LE by D, okay, that is 3400 divided by 400, which gives us a value of how much? That is 34 by 4, 8.5, right? 8.5, okay, 8.5. And since the slenderness ratio is less than 12, it can be considered as a shortcut. So option E is the correct response. So moving forward, okay, we are going to determine the minimum design eccentricity. Okay, so let us calculate the minimum design eccentricity. That is E minimum, right? E minimum, uh, X and Y, it doesn't matter much for a sector column. That is the um, unsupported length divided by 300, uh, sorry, divided by 500. Okay, so that is L by 500 plus D by 30, right? So that is how much? 3400 divided by 500 plus 4, sorry, yeah, 400 divided by 30, which gives us a value of E min as 20.13. So it has to be either 20.13 mm or 20 millimeter, whichever is greater. So we'll take the minimum eccentricity as 20.13 mm. So option C is the correct response. Okay, moving forward, there are two parts to this question remaining. Okay, there are two parts to this question remaining, right? So for the circular column given in question 11, determine the longitudinal reinforcement as per IS 456-2000. Okay, determine the longitudinal reinforcement as per IS 456-2000 if it is subjected to a factored load of 1500 kilonewton. Okay, so here the value of Pu is 1500 kilonewton, and we need to take M25 concrete and Fe415 steel. Okay, consider the reinforced concrete column as a helical reinforcement. Now let us proceed to solve the problem, right? So we have Pu, mhm, Pu is equal to 1500 kilonewton, right? And FCK is 25 MPa, Fy is 415 MPa. Okay, let us consider a circular cross section of diameter 400 millimeter, d is equal to 400, with helical reinforcement. We need to determine the uh, longitudinal reinforcement. Okay, I'm going to copy it to the next slide. So it is given that when, as per clause 39.4 of IS 456, the strength of compression members with helical reinforcement satisfying the equation 39.4.1, right, um, shall be taken as 1.05 times the strength of the similar member with lateral ties. Okay, 39.4.1, it corresponds to uh, the volume of the helical reinforcement. We are going to be designing the helical or the spiral lateral ties as well. Okay, we're going to make sure that it will conform to the clause 39.4.1. Okay, now let us proceed to design the column uh, as per this clause 39.3 and 39.4. Okay, so we need to amplify this strength capacity by a factor of 1.05. Okay, so again we have um, here it can be modified. This particular equation can be modified as about that. Okay, so we can, here this is the actual demand, and then we can reduce the area of concrete proportionately, so that uh, it adds up to this particular PU. Okay, let me clarify that with the example now. Okay, so we have 1500 10 to the power 3 is equal to, again this equation can be rewritten as PU is equal to zero point 0.4 FCK into AG plus 0.67 Fy minus zero point 0.4 FCK into ASC, right? So here what we're going to do is basically this can already we can say that we're going to multiply the RHS by a factor of 1.05, right? So that um, lesser area of concrete and lesser area of this uh, reinforcing steel will be able to withstand the same load. Okay, that is the meaning of this equation. So that is why we are going to consider this factor of 1.05 on the right hand side of the equation. Okay, that is let us proceed to write the values. 1.05 into zero point 0.4 into FCK. FCK is 25 multiplied by AG is pi by 4 into 400 square. That is the gross cross-sectional area plus 0.67 into 415 minus zero point 0.4 into 25 multiplied by ASC. Okay, solving this, we get the value of ASC as, for those who are solving the problem later, I request you to just check this value once again and make sure that you're getting this value, which gives me a value of 641.4 mm square. 641.4 mm square. Okay, so if we are providing, um, you know, a reinforced concrete column which is having concrete of grade M25 and longitudinal rebars of grade Fe415 with the area of 641.4 for a circular column with helical reinforcement, we are able to achieve an ultimate factored load of 1500 kilonewton. Okay, that is the meaning of this, the physical meaning of what you have just solved. Okay, but now let us try to compare whether this area of uh, longitudinal steel, uh, how it compares with the minimum area of reinforcing steel that needs to be provided. Okay, so for a column, we need to provide a minimum of 0.8% of the cross-sectional area. Minimum ASC has to be 0.8% gross area of the circular column. Okay, now we'll try to calculate that value and see how it compares with the ASC that we have just calculated. Okay, let us call it as ASC minimum. ASC minimum is equal to 0.8 divided by 100 of pi by 4 of 400 square. So which gives us a value of 1005 mm square. 1005 mm square, which is much higher than the ASC which we uh, derived for the design. Okay, so the ASC that we obtained for the design is not even qualifying the minimum area of steel, that is 0.8% of the gross cross-sectional area. So we're going to provide a minimum area of steel for the circular cross section, which is 0.8% of the gross cross sectional area, which corresponds to 1005 mm square. Okay, so option D is the correct response. Okay, now let us see this corresponds to how many number of rebars, right? So number of rebars, it can be denoted by N also, right? N is equal to 1005 divided by pi by 4 of 16 square. Okay, let us see how many number of rebars it converts to, right? Which gives us a value of around 5, to be precise 4.99998, which can be written as 5. So we can provide 6 bars of 16 mm diameter. Okay, I'll try to draw a uh, very rough cross section. Okay. Okay, here we have the helical reinforcement, and we need to provide 6 rebars, right? will provide 6 rebars. Six of 16, 5. And it is having a diameter of d is equal to 400. Okay, and this is the spiral or the helical reinforcement which we need to design in the next part of this question. Okay, so in this last question for the day, let us design the helical or the spiral reinforcement for this circular reinforced concrete column. Okay, for the column, it is given that the spiral or the helical reinforcement is 6 millimeter in diameter. What is the minimum spacing that has to be provided as per IS 456? Take FE 415 and 40 mm as the clear cover for the helical ties. Okay. Now let us proceed to solve the problem, right? So we have FCK is 25 MPa and FY even for the spiral ties it would be 415 MPa and the clear cover is 40 mm. Okay, so let us try to find out the value, right? So the ratio of the volume of the helical reinforcement to the volume of core shall not be less than 0.36 Ag by Ac minus 1 multiplied by Fck by Fy. Okay, now let us try to determine the volume of the core, right? Now, before that, let us determine the value of the ratio of spiral reinforcement. Okay, I think the equation is there. The next slide. Okay. Start over here. Ratio of spiral reinforcement. That is rho S is equal to volume of spiral reinforcement divided by the volume of core per unit length of the column. Per unit length of column. Okay, let us find out the volume of core now. Okay, volume of core, that is pi by 4 of 320 square. Okay, because we are substituting 40 mm and 40 mm of the clear cover. Okay, we are going to keep this value as it is. Okay, we can simplify it later on. And then let us find out the volume of the spiral reinforcement. Volume of the spiral reinforcement. Okay, that is given by pi by 4 into 6 square. Okay, that is the cross sectional area multiplied by the that's a cross sectional area multiplied by the diameter or the peripheral length of the stirrup. Okay, the peripheral length of the stirrup, that is given by pi into 320 minus 6 divided by st. Okay, so why this peripheral length is given? Okay, I'm going to just explain it to you. So here we are considering the dotted line distance. Okay, so first we are going to consider the area of this stirrup. Okay, this is the area of stirrup, and here this figure corresponds to the dotted line, the length of the dotted line. Okay, and here st is the spacing between the stirrups. So essentially this equation, that is pi by 4 into 6 square multiplied by pi into 320 minus 6 by st, that gives the volume of the spiral reinforcement. Okay, so now let us simplify this value. I am going to proceed to the next slide. Right, here we have V core and VSPRI, spiral reinforcement. Let us simplify that. Mm. So rho S is equal to volume of the spiral reinforcement, right? Spiral reinforcement divided by the volume of the core, that is pi by 4 of 6 square pi into 320 minus 6, okay, divided by SE, okay, divided by pi by 4 into 320 square. Okay, it is as simple as that. So when we simplify this, we get the ratio of the spiral reinforcement. We get a value of 0.3468 divided by ST. Okay, now we need to equate this value to this 0.36 Ag by Ac minus 1 multiplied by FCK by Fy. From that we can obtain the value of the spacing of the uh, spiral or the helical reinforcement. Okay, now let us start equating those two. I'm going to take a different color now, right? So we have 0.3468 divided by SB is equal to 0.36. Okay. Okay. AG is pi by 4 into 400 square, and AC is pi by 4 of 320 square minus 1 multiplied by 25 by 415. Okay, so solving that, we get a value of ST as 28.4 millimeter. 28.4 millimeter. Okay, so let us look at the final clauses over here. So here it is given that uh, so we have decided that we need to take 6 mm helical reinforcement. Okay, in addition to that, the pitch has to be less than these values, that is 75 millimeter. Okay, I'm going to solve and write it side by side. So for our design, depending on the requirement of the area of the helical reinforcement, or the ratio of the volume of the helical reinforcement to the volume of the core should satisfy this particular equation as per clause 39.41 of IS 456, right? So to satisfy that ratio, we are getting a spacing of 28.4 millimeter. Now let us check with the additional provisions as per the code. Okay, so ST has to be less than 75 millimeter, which it is coming good. It has to be less than core diameter by 6, that is 320 by 6. Okay, that turns out to be 53.3 millimeter. Okay, anyway, our design spacing is already less than this value, and the spacing, in order to avoid the congestion of reinforcement, it has to be greater than 25 millimeter, and has to be greater than 3 times 5t. So 5t is the diameter of the dice, that is 3 into 6 is 18 millimeter. Okay, so the spacing of the dice as per our design is 28.4 millimeter, which is less than these values of 75 millimeter and 53.33. At the same time, it is greater than 25 millimeter and 18 millimeter. So we can easily proceed to say that we can provide uh, lateral ties or the helical ties of 6 millimeter diameter at a spacing of 28 millimeter center to center of Fe415. We can go back and update our figure here, right? So we can go back and update that provide 6, 5 at 28 center to center. Okay, so with that, we have completed the design of short axially loaded coil. So, so the correct response is option B, that is 28 millimeter. Okay. So this belongs to, clause 39.41 of IS 456. So this is a brief recap of today's session. So we considered one frame plan, and we determined the unsupported length of the column. Then we determined the column cumulative stiffness, followed by the cumulative stiffness of the beam along both the longitudinal and the transverse directions, right? And then we determined this flexibility, or delta U by HU, or the story drift per unit story shear, and from that we determined the stability index and classified the frame as a sway versus the non-sway frame. And then we considered the design of the reinforced column with lateral ties, where we initially classified the column as a short column based on the slenderness ratio. Then we proceeded to determine the longitudinal reinforcement, or we proceeded to design the longitudinal reinforcement and the transverse ties. And in the third uh, large example, we considered the design of reinforced concrete circular column with spiral ties. And then again, we uh, classified the column based on the slenderness ratio, then proceeded to design the longitudinal reinforcement and the transverse ties. So in the next week, we're going to take up the design of uh, reinforced column under actual load along with the bending. So I look forward to meeting you all next week. Okay. Thank you all for your kind attention. We will end the session now.